total change, and the fundamental theorem of calculus. So all the work that we've been doing up until this point in this section about area under the curve has been leading us up to something called the fundamental theorem of calculus. So the fundamental theorem of calculus tells us that if f prime of x is a continuous function on some interval a to b, then if you were to integrate that derivative function over the interval a to b, that would give you the total change in the original function between those 2 points. I want you to think about the examples that we started with. When we integrated the velocity, which is the derivative of position, over 2 points, that told us the total change of the position function. So we are able to use the derivative to talk about how the original function changed. We can also write total change as f of b minus f of a without the derivative. Again, think about position. If we had the position function, we could plug in the position at time b minus the position at time a, and that would also give us how much the position changed. So now we're able to write down a distinct relationship that equates both the derivative function and the original function. Before, we were taking the integral of the derivative and we were spitting out a number. But now we're writing it as functions. And this becomes really powerful because if we have information about the original function, we can find out even more than we were able to just using the derivative. So again, the definite integral of the derivative of a function gives the total change in the function. So let's look at some examples and see how we apply the fundamental theorem of calculus to a whole lot of situations. Example 1. Suppose ice is forming on a pond at a rate of dy dt equals the square root of t over 2 inches per hour. If y represents the thickness of the ice in inches at time t in hours since the ice started forming, estimate the thickness of the ice after 5 hours. So here, dy dt, that's y prime. So that is going to be what we're integrating. That's the rate that we're interested in integrating. And we're looking at what's happened over the first 5 hours. So that's time equals 0 to time equals 5. So if we integrate our rate, square root of t over 2 dt, the fundamental theorem says that that's going to give us the total change in thickness between time equals 0 and time equals 5. So we can write that as y of 5 minus y of 0. So some of the pieces of how we use the fundamental theorem are the same as what we were doing before. So here we can compute this definite integral using our calculator. And if we plug everything in, we're going to get 3.726. Now let's talk about the units here. So the rate was in inches per hour, and then time, which we have on the bounds, was in hours. So inches per hour times hours, the hours units are going to cancel, and I get 3.726 inches. So that's going to be the thickness at time 5 minus the thickness at time 0. What this question is actually asking for is the thickness at time 5. So I want to take this thickness at time 0 and I want to add it over. So that means I have y of 0 plus 3.726 equals y of 5. So that means that if I had some sort of initial data about the thickness of the ice, that I would add it to the total change, right? Because again, this is how much my function changed, my thickness function. So here the question is, do I know the thickness of the ice at time 0? Now, it's very reasonable here to assume that at time equals 0, the thickness was 0, because we're talking about when ice started forming. So since we can assume that initially that was 0, that tells me that y of 5 will have to be 3.726 inches. So the thickness of the ice at time equals 5 is just as 3.726. However, if my example had told me something like, initially the ice was 4 inches thick, or initially the ice was 12 inches thick when we started measuring, then my y of 0 would be a different number, and I would be able to get the exact thickness at 5 hours instead of just how much the thickness changed. So we're able to use initial data to help us understand the situation and to find exact values of the original function instead of just how much the original function changed. So let's look at an example where our initial amount is not 0. Example 2. A cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room when time equals 0. The coffee's temperature is changing at a rate of R of t equals -7 to the 0.9 t degrees Celsius per minute with t in minutes. Estimate the coffee's temperature when t equals 10. So t equals 10 is going to be 10 minutes after the coffee has been placed in the room. So if we were to integrate this rate from 0 to 10, what that's going to tell us is the change in temperature over this 10 minutes. And I know from the fundamental theorem that that's going to give me the temperature, let's call that capital R, at time 10 minus the temperature at time 0. So what I'm interested in is the temperature at time 10. That's what I want. I want the exact temperature. So if I were to integrate this rate, this function here, again, I'm going to use my calculator, and that's going to tell me how much the temperature changed. So here, if I integrate that, I get -43.27. So let's talk real quick about units. So the units here of my function were in degrees per minute. My independent units on the bounds here were in minutes. So degrees per minute times minutes. The minutes are going to cancel. So this is -43.27 degrees Celsius. So that's going to be equal to the temperature at time 10 minus the temperature at time 0. So that's the piece we need to figure out. What was our initial temperature of this coffee? So if you look at the first sentence here, we have two pieces of information, and we need to look at them carefully to determine which one is our capital R of 0, our temperature at time 0. So the cup of coffee is 90 degrees Celsius, and the room is 20 degrees Celsius. But what we're talking about in this scenario is the temperature of the coffee, which means that this 90 degrees Celsius is the starting temperature of this coffee. So now I have that the temperature of the coffee at time 10 minus 90 degrees Celsius, our starting coffee temperature. So what we're going to do is we're going to add 90 over to the other side so that we have solved for R of 10. So the temperature at time 10 is going to be 90 plus 43.27. So if we add the 90 over, remember we got to add it because it's subtracted on the right. So when we add that over, we're going to get 46.73 degrees. So the temperature of the coffee at time equals 10 is 46.73 degrees Celsius. And so again, earlier, before the fundamental theorem, I was able to tell how much the temperature changed. So it changed by 43.27 degrees. However, I needed the fundamental theorem to incorporate this initial data, which allowed me to find out the exact value of my function, which is the temperature function, at time equals 10. Let's look at another example. Example 3. The figure below shows the rate of change of the quantity of water in a water tower in liters per day during the month of April. If the tower had 12,000 liters of water, that seems important, on April 1st, estimate the quantity of water in the tower on April 30th. So there's a lot of information here, and then we have a picture that's telling us the rate at which the water is changing. Let's give these functions a name to help us understand what we're doing here. So let's call this Q prime of t, so the derivative of quantity, the rate at which the water quantity is changing. So we know that we're interested in what's happening from April 1st to April 30th. So from time equals 0 to time equals 30, where that represents the days in April. We know that we want to find the area under the curve here. So we're going to find the definite integral for how much the water has changed. And we know from the fundamental theorem that that's going to be the quantity of the water on day 30 minus the quantity of the water on day 0. So what information do we have? What information do we need to find? And what are we actually trying to solve for? So we want to estimate the quantity of the water on day 30. So this is what we're trying to solve for. So if we're trying to solve for Q of 30, that means that we should be able to find values for our integral and our initial quantity. So I'm going to say that Q of 0 is probably the easier piece to find here because that's going to come right from the problem. It says that if the tower had 12,000 liters of water on April 1st, so April 1st is when we started measuring. So the quantity on April 1st is 12,000 liters. So that was our initial quantity, our Q of 0. Now, the change in liters here, how much the quantity changes, we're going to have to use the graph to estimate. So here, we're interested in the area under the curve from 0 to 30. So I want you to remember that any area that's below the x-axis is going to be negative, which means that the quantity was decreasing, and anything above the x-axis is going to be positive. So that would mean that the quantity was increasing. So let's start with the area that's below. So notice that from day 0 to day 12, we have area below the x-axis. So that looks like we're losing water. So if I'm estimating this area, this looks pretty close to a triangle here. So I'm going to use triangles to estimate the area under the curve because it's pretty close. So when I do that, I'm going to do 1/2 base times height. My base here is 12 units long, and then my height is -50. So if I multiply all of those things together, I get -300. And again, it's negative because it's below the x-axis. So that means that from day 0 to day 12, I lost 300 liters of water. And remember, the rate is liters per day, and I'm multiplying it times days, so the days units cancel. So I lost 300 liters of water during the first 12 days. However, from day 12 to day 30, I see that I'm gaining liters of water. So somehow this reserve is being replenished. So now I need to approximate the area under the curve that's on the positive side. So day 12 to day 30. I don't have a very good shape to approximate here. I can't estimate it based on a triangle because I don't really have a triangle here. So I'm going to use a different method to estimate the area above the x-axis. So what I'm going to do is I'm going to look at the area of one block, and then I'm going to estimate how many blocks I think there are here. So I want you to notice that the area of one block, I'm going to make a note over here, one block is 6 units wide and 50 units high, which means each block represents 300 liters of water. So now I have to look at these blocks and try to determine roughly how many there are. So I'm going to start with the whole blocks and I'm going to number them. 1, 2, 3, 4. So there's 4 whole blocks. But then what I need to do is I need to look at how many half blocks and block pieces there are. So I'm going to say that these two together look like they form a 5th block. And then these two together, I don't know how to mark that. Those two together, I think, would form the 6th block. So I'm going to estimate that there's roughly 6 blocks under the curve. I strongly encourage you to only use whole numbers and half numbers, because if you try to make it more complicated than that, then your approximation is going to get tricky. So if one block is 300 units, and I'm estimating that there's 6 blocks, that means that my area here that I'm approximating is going to be 1,800, because again, that was 6 blocks times 300 units for one block. So that gives me 1,800 liters that seems like they've been refilled into this reservoir. So now I have to put it all together. If I have 1,800 coming in and I have 300 that was going out in the beginning, that means that I'm going to net 1,500. So again, I take my positive area and I add my negative area. So the 1,800 plus negative 300 means that this integral is going to be a total change of 1,500 liters. So I've changed by 1,500 liters and I started with 12,000 liters. So now putting everything together, I'm going to line up my equation here. I have 1,500, which is my integral here, equals Q of 30 minus 12,000. So if I'm solving for Q of 30, the quantity of water on day 30, April 30th, I just need to add the 12,000 over to the left. So again, this matches up directly with my equation. So if I add the 12,000 over, I get Q of 30, 13,500 liters. So again, my graph allowed me to find the area under the curve, the definite integral. And then it was my initial information that allowed me to solve for an exact point. Because I knew how much I started with, I was able to talk about the actual value or the quantity of liters at another given time using the combination of the initial amount and the total change. So let's see how we can put this into practice so that we can actually get lots of values of the original function. Example 4. The graph of f prime of x is given below. In addition, we know that f of 0 equals 2. Use this information with the graph above to fill in the following table for values of f of x. Be sure to mathematically justify how you got your results. So here, we have this picture of the derivative. And we already know some relationships about the derivative and the original function. We know that if the derivative is negative, the original function is decreasing. If the derivative is positive, we know that the original function is increasing. But now, using the fundamental theorem of calculus paired with one data point, we can figure out exactly what the value of the original function is. And that's really powerful. So the key to this whole thing is that we know a value on the original function. We know the starting value, f of 0 equals 2. So we can use that paired with this picture to now find the values of the original functions at every point from 0 to 6. And that's really important because that means we could plot those points later and get an exact picture of the original function. We've spent a lot of time going from the original to the first derivative, but this is what's going to allow us to go in the other direction. So how do we use this? So what we want to do is we first want to figure out the value of f of x at x equals 1. We already know the value at 0. So the fundamental theorem, I'm going to come up above, says that if we take the integral from 0 to 1 of f prime of x dx, that's going to equal the original function at 1 minus the original function at 0. So what we're trying to solve for is f of 1, right? The functional value when x equals 1. So what do we already know? We know that f of 0 equals 2, right? That's given to us in the setup of the problem. And that's the piece we really need. So now, if we can figure out how much our function changes between 0 and 1, then we'll be able to find f of 1. So the change from 0 to 1, we can use the graph for. We want to look at the area between 0 and 1 under the curve here. So you can see that this is a nice little triangle here. So from 0 to 1, if we do 1/2 base times height, the base is 1 unit long because we were going from 0 to 1, and the height is -1. So half times 1 times -1 is -1/2. So this integral, the area, is -0.5. So to get f of 1, we're going to need to add the 2 over to the left. And if we add this 2 over here to this -0.5, we get that f of 1 equals 1.5. Now if we want to find f of 2, we need to set up a new integral. But we're going to do it in a similar fashion. So up here, we have the integral from 1 to 2 of f prime of x dx is going to equal f of 2 minus f of 1. So the functional value at 2 minus the functional value at 1. Well, the functional value at 1 is what we just solved for. We know that that's 1.5. So now, if we can get the area under the curve, we can solve algebraically for f of 2. So from 1 to 2, we're looking at the area between the curve and the x-axis, and that's a nice little rectangle. So we're going to do base times height. My base is 1 unit long, and my height is -1. So 1 times -1 is -1. So to solve for f of 2, I'm going to need to add 1.5 over to the left to get that f of 2 alone. And if I add 1.5 to -1, I'm going to get 0.5 as my value at 2. So let's keep going. If I want to find my value at 3, I'm going to do the integral from 2 to 3. F prime of x dx is going to equal, by the fundamental theorem, f of 3 minus f of 2. We know the value at f of 2 because we just computed that. So now we just need to find the area under the curve from 2 to 3. So from 2 to 3, the area under the curve is again a rectangle. So it's going to have a width of 1 and a height of -1. So that area, again, is -1. So to solve for f of 3, I need to add the 0.5 over. -1 plus 0.5 is going to give you -0.5. So f of 3 is going to be -0.5. Moving on, to find f of 4, we're going to do the integral from 3 to 4, f prime of x dx. And that's going to equal f of 4 minus f of 3. F of 3, we know it's -0.5. And to find the area under the curve From 3 to 4, we again look at the area between the function and the x-axis. So here we get another triangle. Triangle is 1/2 base times height. So we have 1/2 times 1 times -1, which is going to give me -0.5. So here we have to be a little careful. So we have f of 4 minus -0.5. So the minus and the negative would cancel. So I'd have f of 4 plus 0.5, which means that when I was bringing it over to the left-hand side, I have to do -0.5 minus 0.5. So when I do that, I'm going to get -1. So f of 4 is -1. And that should make sense because we were at -0.5 and then we were subtracting off another 0.5, right? We were adding more negative area. So it should become more negative, which it does here. So now to get the value at 5, we're going to do the integral from 4 to 5 f prime of x dx, which is going to equal the original at 5 minus the original at 4. And we know the value at 4. We just found that. That's -1. And so in order to get the area under the curve, we look at what's happening between 4 and 5. And something interesting happens here because now we're above the x-axis, right? We've crossed the point where now our area is going to be positive. So when we calculate that area, we're still looking at a triangle. So we do 1/2 base times height. My base is 1 unit and my height is 1 unit. So 1/2 times 1 is positive 1/2. So that area is positive 1/2. And I'm going to bring over the -1. So I have -1 plus 0.5, which means that my functional value at 5 is going to be -0.5. So finally, last but not least, we need to find f of 6. So we can do the integral from 5 to 6 of f prime of x dx equals f of 6 minus f of 5. So f of 5 we know is -0.5. So here, let's do this one all the way out so you can see where the negatives cancel. So we have minus -0.5. Now the area under the curve from 5 to 6, that's a rectangle. It's going to have a base of 1, a height of 1, so a value of 1. Here, the negatives cancel. So in order to bring this over, we have to subtract 0.5 from both sides. So it'll cancel on the right, and I get f of 6 equals 0.5. So now, because I used the fundamental theorem for all of these values, I have all of these points on the original function that I can use to then draw the picture of what's happening. So I'd plot the point 0, 2, the point 1, 1.5, the point x equals 2, y equals 0.5, the point x equals 3, y equals -0.5, so on and so forth. And what you notice here is that from 0 to 4, my function is decreasing because you see the numbers 2, 1.5, 0.5, -0.5, -1. Those are decreasing. And that's exactly where my derivative was negative and I had the negative area. And then from 4 to 6, my numbers were increasing, -1, -0.5, positive 0.5. So we see that the derivative was positive and that the area was positive. So now I have precise points on my original function, so I could plot those points and get a pretty good sense of what the graph of the original function is if I wanted to. But again, the key to this whole thing was having this starting information. That's what allowed us to use the fundamental theorem, and that's what started this whole process. From there, we were just estimating these areas and adding them along as we went. So let's look at one more example. Example 5. Suppose the velocity of a moving object is given in the graph below. So let's take a minute to talk about this graph. We can see that time is in seconds and the velocity appears to be in meters per second. So we have some object that's moving. For the case of what we're going to be studying here, let's assume that positive movement means that we're moving away from a base, and negative movement means we're moving back towards the base or in the other direction. So you can also think left and right. So maybe positive moves to the right, negative moves to the left, but you should think about some sort of directionality in your mind when we start talking about this. So part A, describe the motion of the object over the first 10 seconds. So let's look at where that 10 is. So what I notice is that some of the area between 0 and 10 is positive and some of the area is negative. So that looks like it changes around time equals 4. So between time equals 0 and time equals 4, we are moving, let's say, forward. We're going forward. We'll count positive as forward. And from time equals 4 to time equals 10, we're going to be moving backwards because it's negative. We could also figure out how far forward and how far backwards if we wanted to approximate the area under the curve. So real quick, from time 0 to time 4, I have a triangle here. So if I do 1/2 base times height, my base is 4 units, my height is 4 units. I multiply by half, and I get that that area is 8. So here, not only do I move forward, but I know that it's 8 meters forward. If I wanted to find the area underneath the curve, I'm going to break this up into 2 pieces so that I have a rectangle and a triangle. So my triangle goes from 4 to 8, so that's 4 units for the base. And again, that comes down to -4 for the height. So 1/2 base times height gives me -8 for my triangle. And then my rectangle is 2 units by -4 units. So that's another -8. So I moved forward 8 meters, and then I moved backwards -16 meters. So I was going back in the other direction, -16 meters. So I can get that information exactly because my graph provides values on the x-axis and y-axis. Part B wants to know, what is the acceleration of the object during the first 8 seconds? So time equals 0 to time equals 8 is this line that starts at 0 and decreases all the way until 8. So this line here. And so we have the graph of velocity. And remember, acceleration is the derivative of velocity. So since that's a line, we remember that the derivative of a linear function is the slope of the line. So if we're able to calculate the slope of that line, then we'll know the acceleration from time equals 0 to time equals 8. So to calculate the slope of the line, we're going to use 2 points. So here I'm going to use the point 0, 4, and then I'll also use the point 4, 0. Remember, you can use any 2 points on that red line in order to get the slope. So here I'm going to do the change in y over the change in x. So I have 4 minus 0 over 0 minus 4, and that's going to give me -1. But let's talk about the units. So on the top, the y values, that was in meters per second. And then on the bottom is going to be our time values, which was in seconds. So if you have meters per second divided by seconds, you get meters per second squared. So the acceleration during the first 8 seconds is -1 meters per second squared. So since it's negative, that means that we're going to be decelerating or slowing down. Part C. During which times is the car accelerating, decelerating, and at constant speed? So we're going to be accelerating whenever our derivative of velocity is positive. And so the derivative will be positive whenever our function is increasing. So for acceleration, we want to know, when is this function increasing? So A for acceleration. So we're going to be accelerating. What looks like this is at 12. So from 12 to 15, that function's increasing. So we're accelerating from time equals 12 to time equals 15. And then again from 20 to 24. So again, I'm increasing here from 20 to 24. So time equals 20 to time equals 24. Now we also want to know when we're decelerating. So we're going to be decelerating whenever the slope of our velocity is negative. So here, the slope of our velocity will be negative when our function is decreasing. So that's going to happen from time equals 0 until time equals 8. That red line is the only part on this function where our function is decreasing, and therefore the derivative is going to be negative because it's a negative slope. So finally we have to figure out where we're constant. So we're going to be constant, put a little box here, we're going to be constant whenever our function is horizontal. So acceleration will be 0. So that means our speed is constant. So that happens from time equals 8 to time equals 12. We have this horizontal line. Again, from time equals 16 to time equals 20, we end up with this constant velocity. And then finally, from time equals 24 to time equals 30. So there were 3 places where our speed here, where our acceleration is going to be constant because our speed is steady. Part D. Suppose that at time equals 0, the object is at its home base. How far away from the home base is the object at time equals 4 and time equals 12? So let's draw a picture here to represent what's happening. So let's call this home base. So at time equals 4, let's see how far our position changed. Well, this is something we already calculated in part A. So from time equals 0 to time equals 4, if we look at the area under the velocity curve, that will tell me my change in position. So here we said that that was 8 when we did 1/2 base times height. And again, it was meters per second times seconds. The seconds units cancel and we're left with meters. So at time equals 4, we are 8 meters away from the home in the positive direction, so in the right-hand direction. At time equals 12, let's look at what happened. So we went that 8 meters in this direction, but then we turned around and we're going a whole bunch of meters back in the opposite direction. So we need to figure out the area between 10 and 12. We've already figured out the area before that, and then we can add those all up. So from 10 to 12, that's got a width of 2 and a height of -4. So that's another -8. So it looks like from 4 to 12, we have -8 plus -8 plus -8, which is -24. So I started off going in the positive direction, right? And I walked 8 meters. But then I turned around and I walked 24 meters in the other direction, which is 16 meters away from my home base, because it took me 8 meters to get back to my home base, and then I continued going, and so now I'm 16 meters in the other direction from my home base. So how far away am I from home at time equals 12? Well, I'm 16 meters away from home to the left. At time equals 4, I was 8 meters away to the right. So I'm able to find a lot of information using the fundamental theorem. And this is all really important because we're able to talk about the original function in a more succinct way.